Expected value and variance. In the context of investing, expected value is really referring to the expected return of the investment, and variance refers to the risk of that investment. So our task here is to quantify these variables. Now, our approach will largely depend upon whether we're looking at historical data or forecasted values. What's the difference? Well, with historical data, all these observations have occurred, therefore they get the same weight. So for example, if you're looking at 20 years of historical data, each observation would get a weight of 1/20. However, if you're looking at forecasted values, these values have not occurred yet. So instead, what we do is we assign probabilities or the likelihood of each of these forecasted values occurring. So the only difference, ladies and gentlemen, between historical data bank and estimated or forecasted values is how we construct the weights. Otherwise, the framework is exactly identical. So let's start the process. First, let's compute expected return. Well, if we're using historical data, we simply use the arithmetic average approach. We add up the values of all the observations and divide it by the number of observations. Now, the other way we can restate this is as follows right there. All I did is I took the n from the divisor and turned it into a factor of 1/n. It's the same thing. And the reason I did that, ladies and gentlemen, is because now I can modify this framework for when I'm using forecasted values. And the only thing I have to do, and you can see that right here, so if we were using forecasted values to calculate expected return, the only thing I would change is the weight. So I went from 1/n for historical data to probabilities, because now we're looking at forecasted values. And the same process is going to occur when we compute variance. So if we're using historical data, so first of all, variance is the average dispersion of individual observations around the mean. So what we do is we add up all these dispersions. That's what that says. So add up all the dispersions. And the other thing you'll notice is that we have a square there. And here's why. Because when you're comparing individual observations relative to the mean, some of the observations will be above the mean, some will be below the mean. So if we were just to add up these positive and negative dispersions, they would simply cancel each other out. Well, we don't want that. We want to know the size of the dispersion and not the direction. So how do we make sure the positive and negative dispersions don't simply cross each other out? We square the dispersion. So now even the negative dispersions become positive. So once we do the process in the numerator, i.e. we add up the square of the individual dispersions, then we divide it by number of observations. So again, what I'm going to do is I'm just going to restate this framework. These two are exactly identical. They are exactly identical. All I did is I took the n from the divisor and turned it into a multiple, or factor, if you will. And the reason I did that is because now if I'm using forecasted values, instead of using a weight of 1/n, I could just plug in the probability of each of those forecasted values occurring. So now let's look at an example. Suppose that we have three potential scenarios, and the corporate earnings under each scenario will be different. So there it is. And we're also told the probability of each of these scenarios occurring. So clearly, ladies and gentlemen, what we have here is forecasted values. And what was the giveaway? Well, if they're giving us probability, it means these events have not occurred yet, so they're forecasted values. So naturally, the first thing the analyst wants to know is, well, what's the expected or the average? I have three potential numbers. What's the mean? What's the average, if you will? So there it is. We've got these three events. All we need to know is so it's a weighted average. It's a weighted average. So I just need to know the weight of each scenario, or the probability of each scenario, times the value of each scenario. So I do that for all the scenarios, and I get an average of 7.9 million. Now again, ladies and gentlemen, that's just the average. But the other thing the analyst wants to know is, how dispersed are the individual values around the average? So what we want to know is the variance. And that's what variance is it measures dispersion or volatility relative to the mean. So here's our framework, right? It's right there. It's right there. I showed you the ground up approach in calculating variance using forecasted values. So we just got to apply that. So here's the probability of event A. So again, see how it's lining up. So this is still event A. And this is how dispersed event A is relative to the mean, but remember to square. Now let's shift over to B, right? So what's the probability of B occurring? 50. And what's the dispersion of B from its mean? Again, square. And then finally, event C. What's the probability of event C? 20. What's the dispersion of event C from the mean? It's right there. Remember to square. And then you just add all these up. You just add all these up, and you get 5.89. But 5.89 is the variance. Now remember why we squared. We simply squared so that the negative and positive dispersions don't cancel out. But once we have a value for dispersion, then we can reverse the square by taking its square root. And so that this is referred to as standard deviation. So standard deviation would be 2.43 million. So how would you interpret all the values we calculated, namely 7.9 million for the average and 2.43 for the standard deviation? Our best guess, i.e. the expected value for earnings in the future, is 7.9 million. However, on average, the actual earnings may deviate by 2.43 million from the expected value. And you really have to understand what's going on here. This is just the average. So an astute analyst, like a really good analyst, will say, okay, that's just the average, but how dispersed are the individual observations on average around this mean, if you will? Well, on average, the individual observations deviate from the mean by about 2.43 million.